It's nice to be here, and thank you for inviting me. I'm going to, Mike, I'm going to probably spend more time on that side because I got the remote. So what I'm going to talk about is, what I'm going to do is I'm going to give you an overview of some data converter topologies, talk about problems, talk about, technology, where things are going. Then I'm going to throw an idea out there on taking a mature technology, Deltasigma, and modifying it based on some very fundamental ideas of feedback theory. And then I'll show you an experimental result, and then I'll talk about some other applications. So here's the outline. We won't spend any time on that. So one thing that's happening for the last many years is that the power supply voltage has continued to shrink. However, in CMOS technology, however, the threshold voltage isn't dropping. And so you can see this is a prediction. I pulled this from the ITRS roadmap, and it goes out to 2020. And what you're seeing is that having a lower VDD with the threshold voltage not dropping correspondingly results in problems in analog design, coupled with other issues where the transistors have gains of 10 or less. That would be like the transistor driving its own output impedance, so GMR not R out of the transistor. And then the problems with matching, that's ultimately what is going to be what kills Moore's laws. You can't make two transistors have identical characteristics when they're really, really small. So what we wanted to do with this research was to bring a topic that, or try to use, or try to develop a topology that would still work even though you have horrible matching, say 50% mismatch in threshold voltages or something like that. Now what I'm going to do after the reviews here is I'm going to talk about Deltasigma, and I might do just a qualitative description just to make sure no one goes, well, I don't even know what Deltasigma is, and he's talking about it and I'm trying to figure out. So it'll probably be a little bit corny and off topic, but I think it'll be useful if you don't know what Deltasigma is. Analog to digital converters, the main idea for the last 15 years or so is to try to shrink the interface between, say, an antenna and the digital signal processing. And the best way to do that is to do the A to D conversion right at the antenna. There's lots of applications for A to D converters. I've listed some up here, and the frequency bands of interest. And the key point or takeaway from this slide is that if you reduce CMOS channel lengths, you shrink the technology, you're getting faster speed. And the problem with that is you have to deal with the component mismatches and the reduced gain. And this is kind of an interesting point. If you're given the choice of designing an analog circuit and it doesn't have to be fast, you don't want to use modern technology. If you're doing medical or automotive design and it's traditional low noise analog, you want to stay away from 19 nanometer CMOS because that's not going to help you out. So I think that's one of the things I try to get through when I'm teaching, is the students all fixate on, I want to do something in the smallest technology and that's the best. And no, it's not. The technology isn't as good. You can get higher speeds, but you don't get good gains at low frequency, DC at low frequencies. All right, so quick review of flash A to D converters. This is the traditional way of doing the highest speed A to D converter. You get a flash, your input signal comes in, and you compare it with the reference voltage divided down, and you get a thermometer code here, and as the input signal moves up and down, your 1110 codes move up and down, you code it and you get your word out. The issue is there that the size increases as logarithmically or exponentially rather, and so it becomes very limited for high resolutions. Also, the problems with offsets, and these are serious problems in doing analog design. It's not like ones or twos of millivolts of offset or difference between transistors. You can get nowadays 50 plus millivolts mismatch between two transistors easy, and that's with a 250 millivolt threshold voltage. So the mismatches and offsets, input referred offsets, are becoming more and more of a big deal. And also the resistor mismatch. This topology is great for low resolutions, but again, designing a comparator with a low delay and having a high enough gain to resolve, even for 6 bits, is becoming challenging in the newer technologies. And the result is that you get these shifts in the DC curve and the spurious tones that stick up above the grass when you're looking at the output spectrums and those kind of things. These formulas I reference here, I'm not going to discuss. These, I make some assumptions in my CMOS books, and so I just pull them directly from my CMOS books on what the mismatches are and how good a matching you have to be for the resistors to achieve a certain INL or DNL, and then what's the offsets you can tolerate. Next very common high-speed topology is the pipeline ADC. The pipeline ADC, the way I would explain it to like an 8-year-old is I would say, well, you know, if you want to know something, say a number, you ask if it's above or below some value, and you ask this back and forth until you get an answer of what the number is. And that's kind of what the pipeline ADC does. It's a mature technology using multiplying DACs. You go through and you say, just real quickly, you get sample and hold. Is it above or below, say, the reference voltage over 2? If it's below, you just pass it to the next stage with the multiplication by 2. If it's above, you subtract VED over 2, or your reference voltage over 2, and move to the next stage. You basically get out a code corresponding to your input, and I'm not showing the latency here to make sure all the words sync up. The nice thing here is after a latency of n bits, you get your word coming out, you know, at the same rate you get with the flash. So historically, this has been a really popular architecture because it doesn't take a lot of layout area. I'll put a few slides up here on correction. It's possible to do corrections to get around the errors in the flat or in the pipeline ADC, and it's you can do things with the multiply by 2 stage, like correlated double sampling, removing the offset and low frequency noise, those kind of things. Issue nowadays with using this topology for real high speeds is that if you've got transistors with a gain of 5, an open circuit gain of 5, well, you can't really get the needed gain here to be reasonably close to 2 without significant corrections. Okay? And here it just shows, okay, this is the residue diagram here of what you get if you're in this range. Just output is 0, 1. There's a lot I'm skipping over here because it's not relevant. I'm just trying to provide a background. It's 1.5 bits per, which makes the comparative offsets not an issue, but it shifts the curves. And so what you do is then you take and you put this feedback around and you try to correct UDC errors. And there's all kinds of papers and work that's been done on this. It's quite there's quite elaborate techniques that go into that. John, you told me a few years ago that you guys were doing like some hundreds or something of pipelines on the chip and then doing correction, which blew my mind. So, you know, and effectively getting gigasamples and of performance with high resolutions, I imagine 8 bits or more. So, yeah, 10 bits. So, I mean, this is something that you can do. Now, if you're going to do this as something like a microcontroller where it's supposed to be a tiny bit of the chip, well, this becomes really questionably practical, all right? So we like a high-speed converter that doesn't take a lot of area that could be used with other things. And this is just showing some other issues here with the calibrations that go into correcting for, you know, the errors in the noise and all that. Okay, so let me pause here before I go on any further, and I just want to make sure everybody knows what a Deltasigma is, because that's a kind of a weird name for a very simple concept. So I want you to imagine that you're trying to measure some water going into a bucket. Okay, so the bucket corresponds to the sigma in the Deltasigma. You're going to look at the bucket and say every 10 seconds you're going to decide, is it above or below some arbitrary line? Now, the line is arbitrary, and what that means when we look at the circuits is that the comparator, me, where I'm trying to decide if it's above or below a line, the comparator offset isn't important, because if I pick a line and I say I'm picking that line and I pick a line, you know, a little bit above it, after the startup transient, it doesn't matter. So every time I look into the bucket and I decide every 10 seconds if I should take a cup out, I mark it down on a clipboard. So I might get, if the water coming in was 1/2 cup every 10 seconds, take a cup out, don't take your cup out. Take your cup out, and so you get a 1-bit code, which is 1010. A simple low-pass filter is a moving average filter. You simply average that, and you get a value of 1/2, meaning the water going in is 1/2. Now you can expand that to what happens if the water's moving. If the water's moving slow compared to taking the cup out, you can still track it. You can say, okay, what if I make a mistake and I say, hey, the water's above the line when it really wasn't, and I take a cup out anyway? It doesn't matter because it averages out. The delta is me looking into the bucket, and the sigma is the water, and my decision being summed in the bucket. So that's what delta sigma modulation is that, and so you could think, so that's, for example, this red here, before I talk about the slide, indicates the noise. Notice I have no noise at DC, because if I run the conversion long enough at DC, after a long number of samples, I'm going to get a very precise value for the water going into the bucket. Okay, so it's a very straightforward concept, of a very colorful name to describe a very straightforward concept. And now the key takeaway from all this, if you already knew, or even if you didn't know, is that this process is slow. If I'm going to do an A to D converter, I've got some water going into the bucket, and I'm varying the water that's going in, and I'm going to try to digitally represent how it's varying with the fast 1010 of add or remove stream. I'm not going to be able to move that water very quickly. So why the process is very tolerant to errors in nanometer CMOS, because of, it doesn't matter what the level is, loss, it doesn't matter if I make a mistake because it averages out, etc. It doesn't work fast. Okay, and so we're trying to make sure we can find a way to make this same kind of technique work quickly. Okay, does that make sense? If you didn't know, okay. So here's the idea. So this is where, okay, you take that simple concept. Now I'm going to put all kinds of math into it, and you're going to go, that guy's academic. All right, here's the concept. You have your signal coming in. I just gave the example of the DC water going into a bucket. Here's your bucket. And here's me standing there looking into the bucket. And then I'm going to take my cup, which is this DAC, which I have to fill precisely, because if I'm sloppy, I don't fill it precisely. So that is the one thing that is precise. And that's why we use 1 bit, because it's either full or empty, perfectly linear. I'm going to take and subtract or remove that cup of water from the bucket. Okay, so that's what this represents, and then this 1010 thing here, this digital trace, is going into a filter, which low-pass filters this. If you're a DSP guy, you could use a simple 1 minus Z to the minus K over 1 minus Z to the minus 1 moving average filter. Just a low-pass sync response filter is what a lot of times people use. Okay? So if I look at the spectrums, here's my input sine wave. There's this line right here, if you can represent it. This line right here represents the digital low-pass filter, and then this red here represents the noise, and that represents me not being able to keep up with the averaging as the water's changing quicker and quicker as I increase frequency. Okay, so and of course the noise doesn't magically stop here; it repeats because it's a discrete system. And so we want to talk about this topology, how to implement it, how to modify it practically so we don't, so we can get faster sampling. Okay. So this represents a delaying switch capacitor integrator. I'm not going to go through too much of the details here, but basically here's your input signal. You sample the input signal onto this capacitor when phi1 is high. Sample, I'll just use my finger the old-fashioned way. You sample the input signal onto the capacitor, VCM onto the other side. Then in the alternate cycle, you close the switch capacitor, or this switch is here. And ideally, this side's at VCM, the same as the other side, the op-amp. And you dump the charge that's in excess or below VCM onto the feedback capacitor of the op-amp. So this is my bucket. And then here I am with a, oops, there's a typo there. Here I am with the, looking at the output of the bucket, comparing it to VCM, and then making a decision, is it above or below, feeding back, which should be down, feeding back to this point to remove a cup of water. And you could also do the analogy, if you wanted to be quicker, is you're going to either add a cup of water or you're going to remove a cup of water from the bucket. Okay, and so basically that's what this is. Okay, so your output code is 1010. You maybe change it to 2's complement for +1 and -1, a 0, 1, or a 1, 1. Feed it to the digital filter. Now, and I'll show you this on the next slide. Before I do, actually this might work. I have to use this one, I'm going to run the battery down. So here's the Z domain representation. The output, the total output's here. So the input is delayed by 1 clock cycle, so it goes to the output. That was in the previous slide, that was this thing. And Z -1 is the phase shift, 1 clock cycle. And then this is a differentiator, so it differentiates the quantization noise. And that's important, because when you use a 1-bit quantizer, you got a lot of quantization noise. Now, we don't use multi-bit quantizers, even though we get higher resolutions because we get nonlinearities, okay? That's not to say for the application I'm going to show here that might still not be useful. The benefit then for simple oversampling is that you get, for every doubling in the oversampling ratio, you get 1.5 bits or 9 dB increase in the signal to noise ratio. So this technique is very popular, or has been popular for audio. Op-amp gain can be relatively low on the order of the oversampling ratio. One issue with this topology is you get limit cycle oscillations, so you get things repeating which can cause issues that are unwanted. And you can also get better averaging if you use a second order topology. Your output appears after 2 clock delays, and you use second order differentiate, which means you push the noise to higher values at f(s)/2, but in a frequency band of interest, you're reducing the noise, which is good for a given bandwidth. So you get 2.5 bits, or what's that, roughly 15 dB, if I did math right in my head real quick. 18 dB, or 15 dB, yeah, 15 dB. And increases your effective number of bits. This is a delaying integrator, this is a non-delaying integrator. We just switch the clock phases to get, we can do a delay, non-delaying in the first order. These are all very mature techniques, nothing super new, okay? One thing before we move on, in all of these topologies, I'm going to bring back some basic feedback theory. If you remember the feedback equation, like if the forward path was A and the feedback factor was beta, you write the equation, you get A, or the ultimate gain here, A divided by 1 plus beta AOL, and you divide by A, you get all that. And it basically boils down to that the forward path in a feedback system is much less critical than the feedback path for setting the performance in the gain. So if I use an op-amp with 2,000 gain versus 1,000, I got a gain at 10 op-amp, it's not going to vary very much because the feedback sets the gain. So the key point here is that things in having precision in the forward path is not even remotely as important as having precision in the feedback path. And that's what we're going to exploit here, okay? All right. So, well, why not put multiple Deltasigmas in parallel? I'm going to go through each one of these points. Well, how come we can't use time interleaved sampling and increase the bandwidth and all these things you might think right offhand? Okay, so the first thing I decided to look at is, well, what if I just use simple double sampling where I use one integrator and then I've got 2 input paths, where in one phase I'm sampling the input signal here, phi 1, and in the other phase I sample phi 2, so that I'm basically have me and my clone looking in, half the time I'm looking at it, another half time my clone's looking at it, and you ask, okay, well, what happens with that topology, with the way these phases are set up? And what happens is you end up with 2 noise phase loops leading to 2 noise phases. So in other words, instead of pushing the noise out and recentering the noise on f(s) over f(s), it's still centered on f(s) over 2. We just get a slightly different shape. Okay, and I'll go through this more in a moment. So basically, we don't really get any significant benefit here. I think we get like half a bit for every doubling in the oversampling ratio or something like that. So then the next thought was, well, why not take the Deltasigmas and use some Polyphase DSP techniques? where you're looking at the output of one right after the other here. It's also called end-path sampling. And you basically then think of the Deltasigma as replacing Z with the Z to the K, or however many paths you have. I don't know if you're very familiar with that, but let me just, so when you do this, if you've taken, or you know about digital signal processing, when you put paths in, they're all identical and you plot it like this. You basically think of the one path's Z domain representation being replaced with Z to the K. So let me back up and show you what that means. If I look here, that would mean I would have, for a first order, Z to the minus K, path delays, times 1 minus Z to the minus K. And if you remember, instead of that being a nice differentiation, I'll show you a slide of this, you get basically a roller coaster looking response, okay? And so here's what you get. You get this roller coaster. What we want is what's in the blue. Because if we can get what's in the blue, then we've pushed the noise out to higher frequencies, and we've effectively increased the sampling ratio. So simply by putting, and there's papers that I reference here, there's this paper here that did this and proved what we're saying here. We built it and tested it. So you get a half-bit increase in resolution. You're squishing the noise, but it's squishing it in this area right here. It's not pushing it out like we see right here. Okay, does everybody follow that? Okay, so, so what do we do in order to get around that and get this true noise shaping and get the, use the benefits of Deltasigma but have wider bandwidth conversion? And the answer is we're going to do what's called the K-Delta-1-Sigma modulator. So here's your 1 sigma, and then you've got K-deltas here with the clock phases in the correct way that goes down. And so if you think of this, this takes in this very simple idea. Forward path isn't critical, reverse paths are. So I'm going to put the things that can be a little sloppy in the forward path, the summing of the signals. And then that feedback path, I'll put my K deltas for trying to average what's coming in. Now, of course, if you think about this in the analogy I gave, it's not practical to have 100 people looking into the bucket because pretty soon they don't get out of each other's way. But if you keep the number to a reasonable value and you try to minimize the feedback delays, you can get an improvement in performance. Okay, so it's not like this technique can be heck, I'll just use 100 feedback paths, and oh really, I'll have 100 times, I'll get 100 gigahertz sampling or something like that, right? So there's limitations, but it's still quite useful technique. One reason, nothing's precise and very low power and small layout area. And I'll show you a simple chip we built using this in a moment. Does everybody any questions or comments before I go on? So that's the basic idea.
So the difference between this and the two-phase setup that you had before is that there's not two integrators in this?
Right, this one doesn't have two, well, the other one didn't either. This one is just one integrator. But the phasing of the clocks is slightly different too. This one, and I should talk more about that, because it's an important point. This one, the phasing of the clocks is set by the delay between the adjacent phases. So one problem with this technique is you need to have a delay lock loop or something to generate the phases of the clock. There's applications where you're trying to digitize something over a finite reference and you can simply use 2 logic gates, okay? Benefits here is that if you have mismatch between the capacitors and you have 8 paths, if the mismatch is truly random and not due to a linear variation, then the mismatch will, the variance of the mismatch is reduced by the number of paths you average, and so the matching is more tolerant as well. Does that make sense? Because if you look at the distribution, you average K different capacitors, it squishes the distribution pushes it higher, so you have effectively less mismatch in there. The other thing is that when you do this, if you can use like 2 inverter delays, and you can get like 10 picoseconds in a modern process, your effective sampling rate can then be 100 gigahertz. Well, in a small little area, even if you have imperfections, you're starting with 100 gigahertz, your ability to digitize something at 4 bits or 6 bits using the topology, we have such a large starting bandwidth, is quite high with a reasonable bandwidth in the gigahertz range. Now, if you're going to try to get 10 bits or something large like that, well, I think there may be issues here because, as you'll see, there's interaction where I take this cup of water out, well, that water level's still moving. Well, the next person comes in and goes, oh, it's moving, it's above, and those kind of things can reduce the SNR. But I'll give you some simulations here to talk about those. But the concept itself is quite easy. It's instead of using a time interleaved topology, it's time interleaving in the feedback paths. Okay. All right. Any other? Yep.
This is a more simple question, but I'm an old bipolar guy, and one thing we realized is that while there may be offsets in manufacture, and with are the offsets in CMOS constant with time, regardless of the temperature and other effects?
No. That's a big, so the question was, we're doing it for the tape. Unless they'll get it, do you think the tape will pick it up? Oh, okay. No, that's a big problem nowadays is they have these negative bias temperature instability things, and maybe Frank, you can talk more about that later, I don't know. But things move all over the place, it's crazy. Especially like memories and things, things move around. So if I said yes, they're constant, that would be wrong. Yeah. No, it's a big problem. The manufacturing, how things move around, and all that's a huge issue. All right. Any other questions?
Does that mean that it doesn't make any difference if you do common centroid layout around the spectra?
They don't work nowadays. I mean, if you're trying to get like really, really, really good matching, you can still do common centroid. It'll help. I had a student that was his job, was characterizing matching, and so I learned from him. And he told me that nowadays there's all these other effects that come into play that common centroid doesn't really, they don't even, because they try to use it like in SAMs and things, it doesn't influence or have any impact on the performance of they have to use other things, manufacturing iterations and things like that. Okay, so here's some simulations. This is just showing, and instead of using MATLAB and drawing the smooth traces, I actually did these in Spice and then took long records and just showed that's what the spectrum looks like. And this is one of the things when you look at a textbook and you see a nice smooth noise spectrum. Noise in real life, when you measure it, doesn't look like smooth spectrums unless you average a lot of samples, all right? So this is what a real noise looks like, and if you've ever made noise measurements, that's what the 20 dB that you get 1.5 bits. Okay, so it's just showing, okay, so here's, I had free technology, and so I threw this, I think I built this circuit in like a weekend or something, put the chip together. 1-bit quantizer, 8 feedback paths, so oversampling ratio is 8. I used 100 megahertz clock frequency. It's in half micron, so that's actually a quite high clock frequency. So the sampling frequency new is 800. These were the sensor done. I'll show you the experimental results in a moment. And so the bandwidth 6.25 megahertz. And so the simulation showed 58 dB or 9.3 bits in SIMS. Okay, so you might look at that and go, so what? But for a first order Deltasigma and half micron technology, that's actually pretty impressive. Okay. So what are the issues, because we try to go fast, so you could always say, well, a clock it's slow, and then it'll behave like ideal, and it will, but then that defeats the purpose of using the topology, right? So if you look, there's problems with things charging and discharging, like I haven't fully removed the water, or if I'm going the other way, put the water in the bucket. And then how those things interact with the different paths. So here I've got several slides on this, but it shows representation. I did some sense as well. The representation of how things go and the charge spreading from one cycle to another, and there's approximation. Actually, I had a student do a PhD on this, and he came up with this. So anyway, And you'll see here, there's what happens when you have non-ideal op-amp and also non-ideal spreading of the charge in the feedback paths. And just as you'd expect, the noise doesn't follow ideal, it starts to rise up. And you look at that and go, well, that's unfortunate, but you know what? It's not an error. It just says instead of my signal to noise ratio being 60 dB, it's 58 dB. It's not a catastrophic problem. So it just means your performance. It means I don't get on my cell phone and I can't hear as far away with this data converter in this phone as I could with one closer. So it means it's manufacturable. And then here's what happens when you have delays. There's really no difference if your clock delay of your comparator is T sub s over 2K. So again, that says if you are going to use 16 paths or 32 paths, you really need to design with fast comparators, or else you start getting these increases in the noise. You can see here, this is, keep in mind, this is clock delays at, this is 1/8 of the lower frequency period, the 100 megahertz sampling frequency and so forth. You see the increases. This is a whole clock delay of 5 nanoseconds. In reality, you can't ever use these because you have to put some circuit on the output which gets rid of metastability that says, hey, make a decision now, and then feed that back around so that you don't have these problems, okay? So that's not going to happen. And then, of course, if it adds instead of it removes, you get the benefit of it, of the topology averaging things out. Okay, and so here's some more talking about the delays, quantization delays, and all that. All right, so the test results. And before I forget, and I'll probably mention this again, this topology, say you're going for 6 bits, it's great for very high speed. And one thing I've been looking at lately is SerDes, serializer deserializers, and they go to very high speeds. And so people are predicting that the bang bang PLLs that they currently use are going to run out of steam. And so I was thinking, this topology, if you're running at 6 bits or something really low, but you're getting like 100 gigahertz, clock cycle delay of difference between the edges of 10 picoseconds or less, which is very practical nowadays in these smaller technologies. You might be able to use a topology for doing a simple A to D conversion for a SerDes and then adjust the digital signal algorithms to give you reconstruct the waveform. And I think that's a very practical thing. The problem is I can't even imagine doing anything or measurements at 10 gigahertz digital in my lab. So 100 gigahertz, I wouldn't want the students breathing near the equipment. All right, so this is the chip, and my student, actually, this one, my student laid out, Cajun. And we mounted it in printed circuit board. Pausing because I'm trying to buy a wire bonder right now, so if any of you know any leads on some cheap wire bonders. And one of the issues is, I had great luck with this one. The bond stayed on there for all the measurements. Nowadays, I put a bond on something and it pops right up, and then you do the gold plating and the stripping off and all that. So anyway, I'm very interested in these because it's a way for a real low cost prototyping and testing. Anyway, recognize this, John? Harvested the data from the chip on the board there. I did a little hokey thing here. These resistors, if I remember correctly, are like 510 ohms. So I have a divider there that I reduced the digital levels down so I wouldn't need as big a driver so the chip would drive off. And then they go into the harvesting here and read into the scope, and then once they're in a scope, we use MATLAB to do the massaging of the data. So the only thing that's on this chip besides the driver is the K-Delta-1-Sigma topology itself. Okay, so none of the DSP or any of that. And that way it's powerful, so we can pull things out of the data. Here on the top, there was the simulated. On the bottom, there's the measured results. Everything worked just like we were thinking it should. I thought I had more results than that. Second order, I guess I didn't. Maybe it's in the summary. Oh, I remember the issue. The issue here was we couldn't, we had issues with startup transients and things like that. But basically the bottom line was that it was exactly like what we simulated. Because there's really nothing that complicated in there. So. All right, and then there's the second order K-Delta-1-Sigma, and there's the concise block diagram. I'm going to blow through these last slides and just tell you one of the issues with doing research in data converters nowadays is it's incredibly hard to find somebody to fund you. Okay, so if you write a proposal like NSF, they don't want to fund a data converter design because that's not something that's going to push the edge of the wedge, and that's really, what is the term they use? High risk, high impact kind of thing. So, all right, anyway, so these are just some of the topologies. A concise diagram where you got an array of 8 of these. And simulation results, sure it works, great, you're able to get 80 dB with an effective bits of 13 bits. But again, this is only for the same conditions I showed you before, which was a 6.25 megahertz bandwidth, and you see the noise spectrum here. And I did some other simulations using continuous time because I thought, oh, I did everything in switch capacitors. I wonder what would happen if you use continuous time techniques, which is where I was thinking of like the application for the SerDes. Because you could actually take the resistors, it's hard to see in this thing, you could take the resistors here and connect those to the input pad and have a little trim to adjust the 50 ohm input over all the frequencies, you know, maybe 10 or 20% depending on matching. And then not have any switch capacitors and just have the clocks for the comparators that come in. So the problem there is it's not an analog design problem, it's a digital problem because you have to recombine the outputs of the 8 together where there are very small differences in changing between the outputs. That ends up being not an issue because you can look at these 4 or 2 or whatever while these 4 are changing, and then once you've got them all compiled and digital, then you ship it out and then you have the record nice and steady. So the digital problem is actually a very simple problem for high-speed design. So here's the MATLAB, some of the scripts, and so 8 paths shows what the signal noise ratios are. This is interesting. So serial mode means you recombine the data in a register, you know, boom, 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 boom. The parallel mode means you wait for the 8th path to get done, and then you shift the data out as a sum. So you're summing all 8 paths. And of course that, if you think about it, is nothing, if you sum the 8 bits and then store it, that's nothing more than a sync response filter looking at the 8 paths, you know, sum of 8 paths and so on. And these are all just some background stuff here. I think I've talked long enough. Here's the future research and the benefits. Does anybody have any questions? Please.
It was occurring to me, as I compare going at a very high clock rate with just one comparative feedback and then the lower clock rate with multiple levels of match speed, I'm trying to decide whether the KT over C noise will be identical by the time it's all done or whether there'll be some benefit.
I think there'll be a benefit because each time you sample onto one of those capacitors, right, you're sampling noise, right? So that noise is then sent to the feedback capacitor. However, if you look at it, if the noise is random, and it's Gaussian, and it's not some funny spectral or some funny probability density function, if you average 8 of those sampled noises and they're truly random, it should reduce the KT over C noise by the number you sample.
Except the capacitor sizes will be different than they would anyway. Well, maybe not.
No.
Yeah, I guess I'm trying to decide.
Yeah, no, it should be, just think of it as this way. If you look at the, back here and look at it. If you look at, it's something simpler. This one, if you look at, each time you sample a signal on here, right, you get the thermal noise from the switch, and that varies in this random, this KT over C.
Yeah, because that won't be the same size as it
Yeah.
would have been.
Yeah, but even if you have different, the different size capacitors is an issue because then you're feeding back different signals because your effective cup size is changing from one user to the next. So, but if in the case of the noise, that still wouldn't matter because if you used a bigger capacitor, you just get less KT over C noise, right? And then you dump less noise back in.
Yeah.
But it might affect the distribution.
Yeah, it's just unobvious.
Any other questions?
So I think it's interesting because you're getting past kind of the inherent technology limit the process, right? You're
Yeah.
parallelizing things. So do you have a feeling for, because you're essentially, ideally you're getting like n times better SMR than you would, or not SMR, SM, or n times faster sampling
Yep.
than you would in the technology without doing this, right?
Yep.
So and I figure practically speaking, there are some, you mentioned that there's some effects that there's a parallel and additional loading. So practically speaking, if you how much better, or it's kind of the efficiency of how much better you get out of this. If you can do it if you run this at X speed without it leaving, and you're leaving by 10, like how much faster you actually get.
That would be a shot in the dark.
Okay.
Several things. I did the proof of concept with the switch capacitors. I think if it would be better probably for power and for speed if you didn't use switch capacitors, use just RCs, because they would be super tiny. You would need non-overlapping clocks for all those. So when you put all those things together, it's something that I think would be really easy to test out. But I don't, kind of an academic.
Yeah, I was wondering what the ideality is of how much you.
Yeah, I'm guessing that you could probably is exponential. If you back off the clock frequency, you probably get exact ideal, and then you will get exactly the ideal, and then as you increase the clock frequency, all these things, the sloshing and all that are going to come into play, and things are going to roll off. Now, how fast they roll off, I don't know. Yeah.
Did you generate all of your clocks externally, or was there?
No, that was on chip. We had a DLL on there as well. Yeah, I didn't mention that.
Did it? I mean, have you kind of pushed some of the need for precision onto the clock?
Well, that's a good question too. I kind of rushed over because clock jitter is like a huge problem.
Well, and matching between the phases and.
This like the capacitor mismatch. If you route your clocks with equal delays and the clock is jittery, and again it's got a PDF that's Gaussian in shape, that averaging all the different paths will reduce. It's a common thing in Deltasigma. It will reduce the effects of clock jitter. So if your RMS jitter is 5 picoseconds and you average 9 paths, I'd pick an easy one, then it would be reduced by the square root of 9 or 3. So that's under all ideal conditions. Now there's a couple other things. One, of course, the finite rise times. I don't know how that would come into play. If the DLL isn't producing, because the DLL may not produce a truly random rising edge, right? We may get something with the DLL where, especially if you're putting in an input signal that's synced to the clock frequency, where there's some residual timing issues there. So very big concern. The fundamental thing that you're averaging the clock phases, that's good for data converters, because you're basically saying, okay, if it's here too early on one, it's here too late on the other, then the average and it works out.
Does that make any assumptions about the correlation of the signal to your clocking and being totally asynchronous?
I don't.
As you mentioned, CERTES and systems that were, if the data rate was somehow linked to your clock rate, and you had some non-uniform clocking, you fall in the same periodicity with your signal, and it shows
I can think of all kinds of issues there, so I don't know. I have to take some thought. I think that if you can generate an asynchronous clock for a SerDes application, which is not related to your input signal, but generated the phases of the clock that you need, that you could actually do it with a ring oscillator and just tap off. Of course, there's issues with the phase noise with the ring oscillator, but assuming those aren't a problem, that you just tap off and then asynchronously bring the signal in and look at the digital data coming out, clocked out, and use your DSP to reconstruct, and maybe you can feedback a signal to say, hey, adjust your feedback signal to modulate the amplitude or something like that, where it can be really simple. But as you apparently know, all those clocking issues are really. You can say one thing, oh, what about this? It doesn't work. All right, thank you.